I'm Al-Zayer, and I'm presenting a work, AutoPhoto, Aesthetic Photo Capture using Reinforcement Learning. We'd like to take an aesthetic photo of this apartment. Say we're real estate agents that are trying to sell this property. The composition of this photo is a little off, and we need to improve it. How about we turn the camera a little bit to the right? Perfect, that looks just right. We should capture this photo. So here note that you can observe that the process of photo capture can be done in a stepwise manner, where you're improving the photo composition by moving the camera until you achieve good composition and then capture the photo. So our question is, can we do this autonomously? This would be significant because, for example, for real estate agents, you can just use robots to capture photos instead of hiring professional photographers. And spoiler alert, the answer is yes. That's what we did in this paper. And here we will show a demonstration of our system running in simulation. You can see that it's moving around, doing a little bit of panning, then finally adjusting the composition. Then once it's right, capture the photo. So our problem statement is, given initial camera location, can we move around and capture an aesthetically pleasing photo autonomously? So here's an overview of our major components. First, an aesthetic model that's also being used as feature extractor, a photographer agent that will predict probability distribution over actions, which involve rotation, moving around, and capturing the photo. We'll start by discussing the aesthetic estimation and existing work on it. There are many heuristics for photo composition, like the famous rule of thirds and golden selection. However, it's not clear how to use them in a general way since they require having some sort of predefined object of interest. So one way to go around that is to use a learned aesthetic model instead of you following explicit rules. This will be more general than heuristics, since you can use any image and then you'll just compute an aesthetic score for it. So you wouldn't need explicit rules for composition. And then you can also use that directly as an optimization objective and optimize with respect to the output of that aesthetic model. So there is existing work on learned aesthetics by Wei et al. They collected a large data set of photos and users' rankings, and then they trained aesthetic estimator by training a model to be consistent with user rankings using ranking loss. Then they use this model for automatic image cropping. In this work, we adopt their model for aesthetic estimation. One issue we handle is that since the model was mainly designed for cropping, small camera translations could vary the score significantly. And to avoid that, we added additional loss for translation robustness, where we minimally crop images in the dataset and minimize the mean square difference of the aesthetic score between the original image and the cropped one. This is important because you wouldn't want small camera movement to have significant impact on the aesthetic score, especially with the possible noise that you would have in the action that you would take. We also added ranking loss to ensure that the model ranks well-exposed images better than overexposed and underexposed images. Now that we discussed the aesthetic model that we're using, we'll go into how we design the photographer agent component. So our solution is formulating the process of photo capture as a partially observable Markov decision process. This way we can optimize the model using reinforcement learning. To define partially observable Markov decision process, we need to define actions, state, and a reward function. The actions we have consist of rotation to the left and right with different granularities to allow for coarse exploration and final adjustments for the composition, as well as moving both forward and backward, and a capture action. And the state is the camera view. Note that our setup is partially observable since we can only observe the environment through the camera viewport and can't see the entire environment at once. Now we need to define our reward function. We'll explain each term in their word function. So of course, we would like to capture aesthetically pleasing photo. So we have a sparse reward that's +1 if the image that we capture achieves the aesthetic threshold and -1 otherwise. And since the scene is unknown, we need to do some exploration before capturing the photo. And to encourage the model to explore during early stages of training, we add an exploration reward that decays exponentially during training. That's to encourage the model to take more actions early in the training and avoid terminating early. And we also add a score difference reward to encourage the model to move towards views with higher aesthetic scores by adding the aesthetic score difference between the current view and the previous view. We also want the model to be efficient, since it would be impractical if it takes too many steps. So we add a time penalty that's linear with the number of steps taken. So overall, we have the sparse reward, exploration reward, score difference, and a time penalty. So overview of our model architecture. We have the aesthetic model, and we also use the features after every layer of the aesthetic model, and we feed it to feed-forward network along the LCM layer to predict a probability distribution over the actions. And we optimize the model using PPO, which is proximal policy optimization, an optimization algorithm for reinforcement learning. Note that how would we set the aesthetic threshold? Because the aesthetic scores vary wildly across scenes. So for example, a scene of a messy room would have lower aesthetic scores than mountainous and scenic region. So to do that, we would need to have the aesthetic threshold to be scene dependent. We handle this by setting the threshold adaptively. For each scene and simulation, we sample a large number of views, and then, given initial location, we set the aesthetic threshold based on the nearest views. Specifically, we set the threshold to be a standard deviation above the mean of the nearby aesthetic scores. Our simulation setup is we use Facebook AI Habitat as a simulator, and we train on the Gibson data set and evaluate on unseen scenes from Gibson and Replica. Both Gibson and Replica are data sets of indoors environments, and we use them because they're high quality, but our setup should generalize to any domains with good simulation data. Now to discuss the results, we briefly go over the baselines we compare against. Baselines are random policy that simply takes actions at random, rule of thirds, where we find a salient object in the initial view and try to move the camera such that the object is in one of the thirds of the corners of the view. Imitation learning, where we sample trajectories that achieve the threshold and train a model using behavioral cloning. Keyframe selection, where we perform a random walk, then backtrack to the frame with the highest aesthetic score. And finally, we also compare against the greedy policy that tries all actions and then pick the action that improve the aesthetic score the most. None of the actions improve the aesthetic score, then we capture the photo. Note that we limit all the baseline to a similar number of steps as our policy for a fair comparison. Here we plot the percentage that each policy achieved the aesthetic threshold. Note that for random, accuracy is around 13%, which is roughly equal for what you'd expect when you sample a random view from a Gaussian distribution and then requiring the score to be a standard deviation above the mean. Our method achieved around 78%, while the best baseline achieved less than 55%. So our method significantly outperforms baselines, and it indeed captured aesthetic photos that are consistent with the aesthetic model. Here we show visualization of the initial view against photos taken by our method and the strongest baselines. Note that in the first and second row, our model does explore the environment and tries to find aesthetic views of the scene, even though it's not necessarily the same as the initial view. And the third row, you can see how it's nicely centered the dining table. In this example, can see that the left photo is a reasonable view that someone might capture, but AutoPhoto backs out and then nicely centers the meeting table. Now we discuss deploying our system in real life. We deploy the system on ClearPath Jack UGV. Here you can see a photo of the robot and the camera setup that we used. Here, note that the initial view is in a hallway, and after it explores around, captures a photo of the left title and the left third of the image, which is actually consistent with the law of thirds. And here, it nicely centers the hallway and takes a picture of it. And in this setup, you can see that the system captures a photo that aesthetically framed the staircase at an angle. Since we can't sample random views in the same way we did in simulation, we can't really compare against some aesthetic threshold. So we conducted the user study to evaluate the model performance. We provide the user with pairs of the initial view and the photo captured by AutoPhoto. For each comparison, we set the preference score to be 0 if the user preferred the initial view, 0.5 if they think both views are equal, and 1 if they prefer the photo captured by AutoPhoto. And the average user preference score is 0.63, which indicates that our model is preferred 63% of the time. Now we show videos of our model running to show its behavior in runtime. Here you can see that it's panning to explore the scene, then backing up to nicely frame the bed, and then capture the photo. So here you can see that's quickly turning with coarse turning actions, and then finally adjusting the view before it captures the photo once everything is well composed. And here you can see that it captures action early without the version of 15 that the view is good. And in real life, you can see that also does similar behavior of exploring by turning until find aesthetic view and then capture it. And again, it goes back and forth a bit, and then once it finds a well-composed view, it captures a photo. So in conclusion, in this work, we formulated the process of photo capture as a partially observable Markov decision process. And we demonstrated taking aesthetic photos autonomously in both simulation and real life. Possible directions for future work is, first, to make the system generalize to domains where it's difficult to find simulation data, like outdoors environments, for example. And another direction is to take into account user intent when capturing photos. And at the end, I'd like to thank our funding agencies and everyone who helped us on this project. And thank you for listening.